Hello, everyone. Welcome to today's webinar. I'm Ann Thayer, contributing editor to the CNN Media Group, and I'll be moderating today's event. This webinar is titled Accelerating HPLC, UHPLC Method Development Strategies by Maximizing Selectivity, Exploring Different Stationary Phases, and is being sponsored by MacMod. CNN works with sponsors to identify topics of interest and value to CNN's audience and consistent with CNN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. Before we get started, I'd like to cover a few technical details. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. The presentation today is being sponsored by MacMod. MacMod's mission statement is Smarter Chromatography, which means that it partners with customers to offer innovative solutions to complex problems. The company uses advanced analytical software to match its product portfolio with a customer's separation needs. It leverages 30-plus years of experience in the LC column business and its technical expertise and manufacturing network to help solve the application problems. And it provides up-to-date and accurate technical catalogs and reports from leading separation scientists to keep clients informed of new technologies. During the presentation, we'll hear from Alan McCune, Business Development Director at Advanced Chromatography Technologies. Alan received a PhD in analytical chemistry from the University of Nottingham. His postdoctoral studies involved the development of novel stationary phases and their design and chromatographic performance for use in HPLC, micro-HPLC, and capillary electrochromatography for pharmaceutical applications. He began his career at AstraZeneca, where he was both an individual contributor and supervisor in late-stage product and technology groups, which dealt with drug substance and formulated product delivery, and chromatographic method development, including new separation science technology innovation. Alan then moved to Pfizer, where he became a team leader for chromatography projects in the analytical R&D group for Pfizer's small molecule portfolio. Alan is a fellow of the Royal Society of Chemistry and a chartered chemist. I'll now hand things over to Alan.
Hello and good morning to all of you logging into this webinar today. Thank you very much for taking time to come and listen to this very interesting topic on chromatography. So my contact details are on the slide in front of you. Should you want to reach out to me separately with regards to any questions on the material or chromatography, I'm very happy to try and help if I can. I'd like everyone to note that a PDF copy of these slides will be made available after the webinar. They will also be associated with the on-demand version of this webinar hosted at the CEN website. So today's topic is all around HPLC and UHPLC method development and how we can speed up those method development activities using the power of selectivity. Selectivity being a key concept in chromatography. The focus of the talk today will be about how we can use different types of column chemistries to help us in our quest for rapid method development. So first of all, I'll begin this talk by talking a little bit about, very briefly, what I mean by selectivity, just so that we are all familiar with the terms that I will use. Then I will begin to speak a little bit about method development. How do we do method development? What are the options and different approaches that people tend to use in their laboratories? I'll then move on to talk about how we design new types of stationary phases to maximize selectivity, how we can put together different types of chemistries and chemical groups to give us different mechanisms of interaction. And this really is where we can use the power of the stationary phase chemistry to help us in our method development. And finally, I'll show a worked example where we use different types of chemistries and the power of selectivity with a screening approach to give us options for method development, and how that can provide solutions for the method development challenges that you have in your laboratory today. So first of all, what is selectivity? Selectivity is denoted by the symbol alpha. Sometimes you hear it described as separation factor or separation selectivity. They all mean the same thing. Essentially, you can see from the slide, and this is the classic description of selectivity from textbooks and from Google and various other resources. You can see that selectivity, or alpha, is the ratio of retention factors for two adjacent compounds. Sometimes you hear selectivity can be thought of as peak spacing, those peaks that are next to each other in the chromatogram. And of course, normally our job as chromatographers is to try and separate the different compounds in our samples from each other, hopefully with baseline separation, so we can integrate and quantify those species to understand the complex samples that we're given by our colleagues every day. Now, this is the resolution equation. It's one form of the resolution equation. Now, this isn't a very theoretical talk, and there's a lot of practical data in here, but this is one equation that's quite important. This resolution equation brings together an efficiency term, a selectivity term, and a retention term. And it's actually a very helpful equation for method development. Now, when we look at this equation, it's a mathematical expression. It has symbols and lines. You can see efficiency, N. We can see alpha, selectivity, K, retention. But how do we understand how each of these different parts of the equation contribute to resolution, the resolution of the analytes from each other in our chromatography? When we look at this mathematical expression, it's pretty difficult to understand which part of that equation is powerful. But if we look at the equation in a graphical format, and we can see here on the y-axis we have resolution, and on the x-axis we have alpha, selectivity, N, efficiency, and K, retention, we can see the relationship between selectivity and resolution is almost linear across this range. Selectivity is very powerful with respect to resolution. In fact, it's the most powerful term in this equation. So it goes without saying that selectivity is the key to chromatographic resolution. But of course, the other parameters in this equation are important too. So for instance, efficiency, the number of plates, N, can help boost our performance if we're looking at 5 micron, 3 micron, or sub 2 micron type particles. So selectivity really is the key to resolution in chromatography. If we get the selectivity of our separations right, everything should flow from there with regards to method development. So now we know selectivity is important in chromatography. Which factors affect selectivity? Well, in fact, many of the parameters that you can change and modify in your mobile phase, and even some instrument parameters, have an impact on selectivity, believe it or not. However, they don't all affect selectivity to the same amount. So we can see on the slide at the moment, we have isocratic separations on the left, and the parameters that I've listed in that table are in a list format. So the parameters at the top, so column stationary phase type, pH of your mobile phase, the type of organic modifier, are more powerful with respect to their effect on selectivity than the parameters at the bottom. On the right-hand side of the slide, of course, we have gradient separations, gradient elution chromatography, very commonly used nowadays. The types of samples we get typically have a range of different analytes in them with different hydrophobicities, so it's not unusual for us to need to use gradients to elute species within a reasonable time frame. Now the parameters on the left are just as important in gradient chromatography, but we have some additional parameters specific for gradient analysis. That includes the gradient steepness. We have K star, which is the apparent retention in gradient chromatography, defined by this equation here. Tg, the gradient time, F, the flow rate. We have the gradient range, we have the column volume, Vm, and then we have M, which is a constant depending on the analyte molecular weight. We also have dwell volume, and this can have a very big impact on selectivity when we're moving methods between instruments, and that's another whole topic and another talk all on its own for another day. And then, of course, column dimensions. If we change column dimensions, we affect Vm in that K star equation, which means we affect K star 2 over K star 1, which is selectivity of our separations. So all of these different parameters can affect the selectivity of your analysis. Now, the important thing to think about is from a method development, which parameters should we focus on? Because there are lots of different ways to do method development, and many analysts and chromatographers like to change certain parameters as part of their approach to their method development. But looking at this slide, you can see quite clearly that the column stationary phase is very powerful with respect to its influence on alpha. The pH of your mobile phase is very powerful, and also the type of organic modifier. These are the parameters that give you more bang for your buck in terms of their impact on selectivity. So now we know the importance of selectivity, let's talk about method development. How do we do method development? On the screen now is one approach to method development that I see all around the world every day. We can see that there are 5 boxes there, 1 parameter per box. You can see that also the first bullet point states quite clearly that normally method development is multivariate. It's very unusual to put on one analysis, a couple of injections, and suddenly a method appears in front of you for the analytes that you're interested in. Normally method development is required. We can see from the slide that on the left-hand side, the first box, this is a typical instrument. We have 1 column in the instrument, which is normally a C18, dominated by hydrophobic interactions, the most popular column used all around the world in most market sectors and most application areas. This column and this instrument normally has 1 temperature, 1 mobile phase pH, which is normally acidic. This is the most common place for people to start method development, and 1 organic modifier. Sometimes it's methanol, sometimes it's acetonitrile. It normally depends on the analyst. So we get our sample that we need to do some method development, we put it on the instrument, and normally we perform a broad scouting gradient run using the column, the temperature, the mobile phase that's in that box. We then get the data, the chromatogram from the first couple of injections, and we start to make choices and decisions about what we want to do next. Now, if that first scouting gradient run hasn't given us the separation we're interested in, what do we do next? And you can see underneath that first box, I have 2 times Tg. So if that initial gradient time, that initial gradient analysis doesn't work, normally people will try a different gradient. They might try an isocratic hold, they might try a different gradient slope, something that might try and tease apart the peaks in their samples in their chromatogram. If that doesn't work, what do we do next? And here we have on the screen, for instance, some people look at temperature, low temperature, high temperature. Some people look at solvent type, methanol, a protic solvent, and acetonitrile, aprotic solvent, different allotropic strengths, different impacts on selectivity. Some people will also look at different columns, and I've listed 3 different types or groups of columns on the slide there. We have alkyl chain-based columns, so these are dominated by hydrophobic interactions. C18 and C8 are very common. We have aromatic type stationary phases, for instance, phenyl, and we have other types, extended phenyl, even pentafluorophenyl type phases. And then we have polar type phases as well. So I'm not including things like ion exchange and those type of phases here. So we have polar interaction type phases. That could be like a polar embedded phase, such as the C18 amide, for instance. And then on the right-hand side here, we have pH. So low, medium and high pH. All of these different parameters are options for our method development. And of course, as we perform injections and we change one of these parameters, we gain new chromatograms, we gain new knowledge with respect to our method development. But of course, it takes more time. And whilst we're generating useful retention knowledge, are we getting closer to our final method that's suitable for the analysis we're interested in? So possibly there are lots of different runs that you can perform. And as I'm sure you all know and you've all experienced, sometimes method development can feel like it takes a long time, and other times maybe it doesn't seem to take too long at all, maybe a couple of days. But this is an iterative approach to method development, one factor at a time approach to method development. Now, of course, what would be helpful, and if we consider selectivity, we can do this, is if we reduce the number of parameters that we explore during our method development, if we think about those parameters that have a big impact on selectivity. Now, for the talk today, I'm going to focus on different types of column chemistries, how they affect selectivity, and then use a real example to show how we can use it to our advantage in method development. So before I go into the method development example, let's look at different types of stationary phase chemistries. How do we design different types of chemistries? Now, as I said earlier, the C18 chemistry is the most popular phase used all around the world. But what about other types of phases? So here we have an aromatic phase. We have a simple aromatic ring, and if we substitute onto this ring different types of chemistries, and here I have electron donating group examples, we have some amines, some alkyls, some alkoxy type groups and other types of aromatics and so on, we change the properties of that ring system. So here in the picture you can see we have an alkyl phenyl type stationary phase. Now you can see that the properties of that ring have changed. They become slightly more electronegative. There's a weak dipole across that ring. We can also do the opposite to that, and we can substitute onto this ring system different types of electron withdrawing groups. And here we have the pentafluorophenyl as an example. 5 electronegative fluorine groups substituted onto the aromatic ring, which of course have an impact on the properties of that ring. And you can see there's a dipole, moderate dipole moment now on that ring with an alkyl chain also attached to it. Now, why is this important for new stationary phase design? Well, the thing we're interested with stationary phases are the mechanisms of interaction. And by substituting different types of functionality onto these aromatic rings, we can change the weighting of the mechanisms of interaction. So for instance, the alkyl aromatic stationary phase, such as the C18AR, which I've put on the slide there, is a combination of a C18 chemistry and a phenyl type chemistry together in a single stationary phase. So we have the hydrophobic mechanism of interaction from the C18, but we have the pi-pi system interactions and a weak dipole interaction from the phenyl stationary phase. So this is quite different to the standard C18 chemistry. These different mechanisms of interaction give us different selectivity compared to a standard C18. And the same discussion with the C18 PFP. We have the hydrophobic mechanism of the C18, but we have those other mechanisms from the pentafluorophenyl group. We have the aromatic interactions, we have the moderate dipole, all together in a single stationary phase. But not only that, but these different types of stationary phase have advantages over standard C18 chemistries too. Both of these chemistries, for instance, are 100% wettable. This means that with these types of stationary phases, these types of columns in your instrument, you can use 0% organic solvent. So that means that if you're trying to retain polar compounds in your mixtures, you can drop your organic solvent to 0, 100% aqueous, to try and retain the polar species in your samples. So these provide advantages, as well as those other mechanisms of interaction. As an example of what the chromatography looks like, of course, all of these material design perspectives are interesting, but how does this affect our chromatography? So on this slide, in the center chromatogram, we have the C18 as the benchmark. The bottom chromatogram, you see we have a short chain phenyl, different selectivity, quicker elution of the analytes as the hydrophobic interaction is much less. Whereas with the C18AR, with the extended alkyl chain, phenyl stationary phase, we get separation of all the compounds in this mixture, and we get a very different selectivity. So the C18AR is almost like bringing together the mechanisms of the C18 in the middle and the mechanisms of the short chain phenyl at the bottom together into a single stationary phase. The C18PFP is an interesting stationary phase because it can provide separation of very closely related, structurally related compounds. So we can see on the screen there that this is a mixture of methoxybenzene isomers. So these are regioisomers or positional isomers. Now, when we analyze this mixture of positional isomers on a standard C18 at the top, you can see we get coelution, and this is exactly what we would expect. Now, the middle chromatogram shows a short chain pentafluoride phenyl stationary phase, and you can see they elute much more quickly than C18, but you can see the selectivity is very different. There's almost complete separation of all the compounds in this particular mixture. Now, if we combine the mechanisms of the PFP together with the mechanisms of the C18, with the C18 PFP, you can see we get a broader retention window. We get full separation of all of these closely related, structurally related regioisomer compounds. So the PFP is a very useful type of column to be used, for instance, in drug substance analysis, raw material analysis, metabolomics, retention of polar compounds. This phase is used a lot in this area. Other types of phases and phase chemistries that provide different mechanisms. So this is an example of a polar embedded phase, and you can see here that we have the embedded amide group. The difference with this particular polar embedded phase is we have a longer extended alkyl chain spacer between the polar embedded group and the silica particle. This gives this phase stability. In fact, this polar embedded phase can be used at 60 degrees for a month in phosphate buffer, so it's a very stable stationary phase. And also we can design other types of chemistries based off the similar sort of concepts. So at the bottom there, we now have the cyano-ES phase. This is a stable cyano phase. We use the same design concepts where we have a longer alkyl chain with a terminal nitrile group, so we can bring together the hydrophobic mechanism of the alkyl chain together with the mechanisms of the terminal nitrile into a single stationary phase. This is a stable cyanochemistry. These phases, again, are also 100% wettable, so they can be used in 0% organic for the retention of polar compounds. So what do these phases do chromatographically? Well, here we have a simple example. On the top, we have the C18 amide chemistry. You can see we have these polyhydroxy aromatic, sort of mid-polar type compounds, relatively well separated and retained. Whereas under exactly the same conditions, using a C18 chemistry, we can see all of these compounds elute much more quickly with poorer separation and resolution. And so the C18 amide chemistry providing those different mechanisms of interaction to help us with separation and retention. The last phase I want to talk about and then move on to some method development examples is what we call the super C18 chemistry. So this is a stationary phase that's stable between pH 2 and pH 11. So should you need to explore a wide pH range, this type of chemistry is ideal for that job. Now, with normal C18 columns, they're normally quoted a stability range of pH 2 to pH 8. When you get into the alkaline region of the pH spectrum, you begin to dissolve silica particles. And if you've ever tried using standard C18 columns at pH 8 or 9 or 10, you see that you get a few injections out of the column, but then quickly the column degrades. You start to get poor peak shape and eventually peak splitting. And what actually happens is the silica particles are dissolving and the column then must be thrown away. It's not you can't clean it and save it. This type of phase, the super C18, is designed to be as stable in the alkaline region as it is in the acidic region. And there's various data which shows that at low pH, mid pH, or high pH, this type of column is excellent and very stable. Now, why do people use different pHs? Well, because they want to look at selectivity. So here we have an example of a low pH separation for this mixture of acid, basic, and neutral compounds, and then the same analyte mixture at high pH, using the same method conditions, just using ammonium formate at low pH and using ammonium hydroxide at high pH. And of course, we get a difference in retention and selectivity. Our ionizable compounds, acids and bases, when they gain and lose protons, their retention changes significantly in reverse phase chromatography. When they're charged, they're polar, they elute more quickly. When they're uncharged or neutral or ion suppressed, they retain more in reverse phase. So pH can be a method for also changing the selectivity of your separations. This is just a specification sheet if anybody's interested in the finer details of the different columns that I've talked about. So what does this mean for method development? Well, what we've done with the different chemistries that we've developed is designed chemistries that have different mechanisms of interaction. So we've used what's called the Tanaka protocol, and at the bottom I've written that there, the extended Tanaka protocol, to characterize the 6 different columns on your screen. And we can understand using the Tanaka protocol, this was published back in the, I think it's the 1980s or 90s, using a series of different tests. You run these down your column, and then you take ratios of different analytes, and it helps you understand the weighting of different mechanisms present on that column. So we can see, for instance, I've highlighted here in the red box a standard C18, and there are 5 mechanisms of interaction which we can understand from this test. So you can see we have hydrophobic interactions, pi system interactions, dipole-dipole interactions. Apologies, oh, there we go, the screen came back. Dipole-dipole interactions, hydrogen bonding, and shape selectivity. Using the Tanaka test, we can understand the weighting of these mechanisms. Now, you can see for the standard C18 chemistry that it is dominated by hydrophobic interactions, and of course we all know that. A C18 is an alkyl chain, 18 carbons long, bonded onto a silica platform, and so that mechanism is dominant with all C18 columns. As we move across the table, you can see, of course, there are no pi-pi interactions because there are no aromatic functional groups with a C18, so there's no pi system interactions. There's also no polarizable functionality with C18 columns, so the dipole-dipole interactions are not present either. However, there is some hydrogen bonding with C18 columns, and this is because your analytes can hydrogen bond predominantly with the surface silica silanol groups, which are present with all silica stationary phases. So there's a small amount of hydrogen bonding as a mechanism of interaction present with many C18s. And then finally, most C18s have shape selectivity as well. And this is because your analyte can move between the C18 chains, and if your analyte shows different shapes or potentially conformers, then you can get a degree of selectivity of the shape from many C18 columns. So there are 2 stars to indicate there is some shape selectivity. Now, of course, from a method development perspective, we don't just want to use C18 columns. We want to use different columns with different chemistries and mechanisms of interaction, because more mechanisms of interaction means our analyte can be retained or separated from the other species that are within our samples. So it makes sense when we're doing method development to use different chemistries with different mechanisms of interaction. And the 6 different columns that I've listed on the screen there all have the different weightings of different mechanisms to help us in our method development. So if we look at this, for instance, using acetonitrile as a single organic solvent, we can see with the different column chemistries, they have complementary selectivity to each other in acetonitrile at 1 low pH. So this is, if you like, if you use a column switcher, This is like a screening or method development platform. Now, normally, and what I do and we do in my laboratory is we actually have a solvent switcher and a column switcher. So we're able to use 6 different column chemistries and also 2 solvents as part of our screen. So we have the 6 different ACE chemistries, but we also have the protic solvent methanol and the aprotic solvent acetonitrile as part of our screen. So we actually have a 6-column, 2 solvent, normally 1 low acidic pH screen as our standard platform for all method development that we do. And this is our standard approach, our screening protocol, semi-automated screening protocol that we use for method development. And of course, this is based on selectivity. We're using the power of the column chemistry with the 2 different properties of the 2 organic solvents to help us resolve our compounds from each other. And I'll show you an example now of how we can use this as part of our method development strategy. So if we consider the 5 boxes that I showed you earlier with the different parameters, we can actually reduce those boxes now just down to 2 parameters. We have column chemistry and we have organic solvent. So we've greatly simplified, and if we have the equipment, we can automate with column switches and solvent switches. We can automate this column screening process. This gives you productive method development. So this is the instrument that we use in my lab. We have a UHPLC instrument. We have the column oven next to the instrument with 6 different column chemistries in the oven. Now we use a standard format of 100 by 3 millimeter column dimensions, 2 micron. We found this to be a very robust format, gives good column lifetimes, but also it's relatively quick in terms of the screening approach. So it means we can turn our method development around quite fast. So how do we do method development? I'm going to work through an example now, and then we'll be coming towards the end of the webinar. So there are 4 steps, and I'm going to talk about step 1 in the method development approach. So we normally do some scouting runs with general starting conditions. This gives us an understanding of the retention behavior of our analytes in our samples and how the different solvents and column chemistry combinations are helping us or not with our separation. Then there's step 2 where we optimize the chromatography. We then validate depending on the industry you're in, and then we begin the sample analysis, or we transfer the method elsewhere in step 4. So first of all, what are our initial gradient method development conditions? So normally we perform a broad scouting gradient run. So this gives us a good understanding of the retention behavior of the analytes in our samples. Are they polar, mid-polar, or non-polar, depending on where they elute with the different column chemistries. Normally, we always start at acidic pH, again, unless our analytes or the application indicate otherwise. How do we calculate our starting conditions? Well, we use that simple equation that I showed you previously, the K-star equation, and we can solve this equation because we know we can give K-star a value. So we want the retention of our analytes in this example, for instance, to be greater than 2 and less than 20. So we know K-star, and we know the maximum pressure of our instrument. We know the column dimensions, so we know the VM term. We know the gradient range. So we can solve the equation for the gradient time and the flow rate, depending on the capabilities of the instrument and the back pressures that we are allowed. So the example I'm going to show you today is acetaminophen in the US, or paracetamol in Europe, and some of its related substances and degradation products. So you can see here we have a mixture of 10 different components. The acetaminophen will be the parent compound, and the other 9 impurities are spiked in at 0.1% to be representative. Now we can see that because this is a very well-known compound, we have the structures of these analytes. We also have some of the physicochemical data too. We have ionization constants. We understand the log P, or values, the measure of lipophilicity, and we can even determine, or we can look up in reference tables, log D values, the distribution of different forms at different pHs. Now, whenever we begin some method development, normally there are two situations. Either we're given a sample and we know what's in the sample, or we're given a sample and we know only something of what's in there. Maybe there's lots of different things that we don't know. Now, in the second situation, we would do a broad scouting gradient run under acidic conditions, and our method development would begin there. In the first example, where we know what's in our sample, it's important that we analyze the characteristics and properties of the analytes. And this is a good example. This is a compound, and there are a number of impurities that we know the data for. We know the physical and chemical data. So it's important to assess each of the compounds to make sure our conditions are appropriate. Now, this is also a good example because one of the compounds here has a property that we need to be careful of. We can see here that 4-aminophenol has a log p-value, a measure of lipophilicity, that is negative. This means that it's highly hydrophilic. Is a very polar compound. And in fact, this compound is so polar that it's not retained in reverse phase chromatography under acidic conditions. And so for this example, we actually need to change our starting conditions, because we can see here from the log D data that as we increase the pH, the polarity of the compound reduces. So if we increase the pH of our mobile phase, we should get some retention of this compound. And of course, we have to retain all of our compounds so we can integrate them and quantify them. It's not helpful for us to have analytes eluting on the solvent front, and conversely, it's not useful to have analytes stuck on the column. We need to see everything so we can integrate it and quantify it. So this is a good example, whereas ordinarily we always use acidic mobile phase, which is normally ammonium formate at pH 3. In this example, we're using ammonium acetate at pH 6. So we weigh out the individual compounds, we dissolve them, we make them up, we filter the sample, we put it on the instrument, and we press go, and we walk away. Now, our instrument is set up as a screening system, so all the methods are already written, the sequence executes, and we get 2 sheets of paper that come out on the printer next to the instrument. One sheet of paper has 6 chromatograms on in methanol, and one has 6 chromatograms on in acetonitrile. And we can very simply, there's a simple stack plot, we can assess the data to see what we need to do next. And that's the data I'm going to share with you today from the instrument. So we've performed the analysis, and these are the data in methanol. So the first thing to note here, so here are the 6 different chromatograms, each of the different column chemistries. Starting at the top, we have C18, AR, PFP, the super C18, the C18 amide, and the cyano-ES. Now, if we look at the chromatograms, it's important as chromatographers, we need to assess the data. We can see, first of all, peak 2 is the 4-aminophenol. And you can see that it is retained. The K value is low, but it is still retained away from the T0. So using the mid-pH, the pH 6 mobile phase was important because it gave us retention of that compound. Now let's look at the chromatography. If we look at peak pairs 1 and 4, you can see if we start at the top, we have co-elution of those compounds. And then with the AR, we have peak 4 eluting on the tail. With the PFP, it's co-eluting. With the super C18, it's co-eluting. With the C18 amide, the polar embedded phase, you can see peak 4 elutes before the parent compound. So a different interaction, different mechanisms, different elution order. And then with the cyano-ES, at the bottom, you can see that peak 4 elutes just about off the tail of the main compound. Now, if we look at peak pairs 7 and 8, we can see they're quite well separated. And we can see that as we start at the top, the C18, 7 and 8 are very well separated, big selectivity value between the two. AR and PFP, very well separated, all good. And even with the super C18, very well separated. But then when we get to the polar embedded C18 amide column, we can see we have a reversal in the elution order. So that polar embedded phase is definitely providing us different interactions for this mixture of compounds. And then at the bottom, the cyano-ES also has a reversal in peak 7 and 8. So the selectivity is quite different for those last 2 column chemistries. And then finally, peak pairs 9 and 10. If we start at the top and go to the bottom, we can see co-eluting, completely co-eluting, partially resolved, co-eluting, and then the C18 amide, 9 and 10 are well resolved, and also on the cyano-ES they are well resolved. So if we add up the number of peaks that are separated across the 6 different column chemistries, we can see we've got 2 chemistries where we have complete separation of all 10 compounds in our mixture. So we haven't done anything else in terms of method development or chromatography tweaking. We have 2 options where we have full separation of all of the compounds in this mixture, which is fantastic. So showing the value of the screen with the different column chemistries. However, a really important point with this slide is most people would have started, of course, with a standard C18 column. And you can see the red box is around the C18 column. And as you can see from the chromatography, we had elution of peak pairs 1 and 4, and we had a co-elution of peak pairs 9 and of peaks 9 and 10 in the pair. So we would have needed to do further method development, further injections, tweaking the gradient, tweaking the temperature, whatever it is you do for your method development to try and get full separation of all 10 compounds from each other. Whereas with this simple screen, using chemistry to maximize the selectivity, you can see we have 2 options for full separation. So that's the first 6 chromatograms. What about the acetonitrile data? So if we flick over to acetonitrile, we can see again peak 2 is retained, which is good, so we can integrate it and quantify it. And then if we look again at the similar peak pairs, 1 and 4 you can see are separated with the C18, separated with the AR, on the tail a little bit with the PFP, separated with the super, co-eluting with the amide, separated with the cyano-ES. Now 7 and 8 and 9 and 10 peaks start to mix together. You can see that if we start at the top, the C18 we have co-elution, the AR we have co-elution, PFP is separated, the super C18 is separated, the C18 amide is separated, and the cyano-ES is also separated. So if we count up the peaks that are separated with the acetonitrile organic solvent, we have 4 options now, and 2 from the previous methanol slide, making 6 different options of column chemistries that would have given us our separation. And again, with acetonitrile, we have co-elution. Peaks 8 and 9 co-elute, further method development is required. So, with this simple example, what I was trying to show you and explain is how screening using the power of the stationary phase chemistry is very helpful for your method development. You set it up, you walk away, it's semi-automated, and you're letting the selectivity and the chemistry do the work. Now, of course, it doesn't always work like this. Oftentimes we do our screens and we do get options for method development, but sometimes you have complex chromatography or peaks that just don't appear to want to separate, even with different chemistries and solvents, and further work is needed. However, the point from what I'm trying to show here with this example is at least if you run your analytes with different chemistries and solvents, you're using chromatography theory to try and help you get the best start in your method development activity. Hopefully you'll have an option from your chemistry and solvent combination, but if not, there should be a better starting place than if you just simply started to do some injections and tried to do your method development from there. Now, we have a method development brochure which gives you more information on the phases that I've talked about, and also you can see there the table of mechanisms of interaction is also within that brochure to help you understand the different column chemistries and how we design them. So just bringing the talk to a close now to give us a chance for Q&A and so on. Hopefully what you've heard today is selectivity is really important in chromatography. If you get the selectivity right, your method development is much easier from there. If you understand selectivity, you can focus on those high impact variables for your method development. So for instance, it's good to focus on column chemistry. It's good to focus on organic solvent type. These are powerful parameters that can help you with your method development, and they can be set up in an automated fashion as well to screen your columns with your samples to try and give you a method from your screening system. I talked a little bit about stationary phase design and how we design different chemistries with different functional groups to give us different mechanisms of interaction. And that's really important because those mechanisms of interaction are going to help you with your selectivity and your separation. I showed you the screening approach, and this is the standard approach we use in our lab. It's not the only approach. There are other ways, of course, to do method development, but we found this to be the most helpful because whatever happens, you get retention, behavior, information from different chemistries in your samples. This helps you make informed decisions for your method development. And finally, I showed you this optimized method development platform based on selectivity, where we use 6 different columns and 2 solvents together to give us, with the example I showed you, options for a method to take forward for further analysis. We have lots of different applications and descriptions of separations of different analytes. And if you are interested and you download the slides, the PDFs, you can see at the bottom of the slide there I've provided a link to the online version of our application guide. This currently has hundreds and hundreds of different applications with a very interactive analyte index, so you can type in something you're interested in, and hopefully there's an example or some starting conditions in there for you to have a look at with ACE phases. So thank you for your attention today. I'm pleased that you listened to the talk. I hope you found it useful. In the USA, you can see that the ACE portfolio and ACE columns are available from MatMod Analytical, and their website is there on this last slide. Now, I've been asked now to do a couple of polls. If you can hang on for a few more moments, I'd like to ask you some poll questions, which will be very useful for us to understand you and how we can help you with your separations. So I'm hoping now that the poll is on your screen, and I'll give it a few more seconds whilst the data is collected. Hopefully, if you can please click one of the answers. This first question is, do you perform HPLC/UHPLC method development? This is useful for us to understand how important this webinar was to you and your interest in the different column chemistries and so on, and whether some of these solutions that we've discussed could be helpful for the type of separation challenges that you have in your laboratory. So that's the first question. I'm hoping now that people have voted. I'm just going to just type in a quick question there, just so that I can try and see if people have voted. Hopefully you have voted. Please do vote, it is important. Oh yes, excellent. I've got a response to say that people are voting. Thank you very much. Thank you very much. The information is useful to us. Okay, I'm just going to give that a few more seconds, and then I want to switch on to the second question. Thank you very much. We will be moving on to the Q&A session next. I can see that we've got a number of different questions that people have submitted. Thank you very much for that. So I'm going to go to the second question now. So the second question is, would you consider novel HPLC/UHPLC chemistries in your method development? So based on the information that I talked about today, those different mechanisms of interaction and how we feel they can help in a number of different separation challenges across many different application areas, is this something that you think is useful? Would you consider this for your method development? If you could vote, that would be really, really useful, please. Again, as I said, it's just useful for us to understand, to make sure that we're doing the right things, providing the right data, the right information to the different customers out there in the different application areas. We want to make sure we're providing the right solutions that are going to help you do your job more effectively. But just a few more seconds on this one. Question 2, would you consider novel HPLC, UHPLC chemistries in your method development? That would be great if you could answer, please. And there's one last question. Thank you for your patience, and then we will go to the Q&A session. So the last question, thank you to everybody who's voted so far. The last question is, would you like somebody to contact you to discuss ACE method development kits? This is just so that we can make sure we provide you with the information on the different chemistries that I talked about today, so you can see some of the data with those different mechanisms of interaction. And also with the different method development kits, one thing I didn't mention in the webinar, because this is a technical webinar, but the method development kit actually provides 3 columns for the same price as a single column. That is on the brochure, and it will be made clear to you if you request the information and look at the brochure and all of the different information on the chemistries and so on. So a few more seconds on this one. So if you can just answer that question one more time, that would be great, please, and then we will go to the Q&A. Would you like someone to contact you to discuss ACE method development kits? So if you think, for instance, the C18AR, the C18PFB, that polar embedded phase, could provide you with options to some of the challenges that you get in your laboratory. Maybe you'd like to set up a screen in your laboratory to help you with your method developments. So if you want us to send that type of information to you, that's brilliant. We have very nice brochures with lots of data and information to help you make your choices, help you understand a bit more about the products. So with that, I am going to now finish. So I'm going to hand back to the moderators and the people who are running the fancy software that you see in front of you. Thank you very much for listening once more, and I'll be very happy to try and answer some of the questions which many people have sent in. So thank you very much.
Thank you, Alan, for that very interesting presentation. We'll move to Q&A. A lot of questions have come in. Just want people to know that if we don't get to them today, that we can follow up later. A question that came in early on, referring to one of your earlier slides. Someone says asks that they've always approached development by addressing chemistry prior to physics. That is, the type of stationary phase, the organic solvent choice, before things like considering temperature, gradient profile, and column dimensions. This person believes that the physical parameters may have more predictable outcomes. It seems that you've listed these as 3rd and 4th in your experiments, and the person asks why.
Okay, so thank you for the question. I'm hoping everyone can hear me now. I've just taken myself back off mute again. I guess, as I said, there's many different ways to do method development. There isn't just one single way. From my perspective, and I am a practicing chromatographer, I've always looked at column chemistry because it all focuses around selectivity. Now, the parameters that affect selectivity are listed on that slide. If you look in textbooks, if you Google selectivity in chromatography and so on, there are distinct parameters that we can change and modify in our mobile phase, in our chemistry, in our instrumentation, hardware, and so on, that all impact alpha. Now, when we're doing method development, I showed you the resolution equation and how selectivity has the biggest impact on resolution. And don't forget, what we're trying to do is resolve compounds from each other. So it makes sense when we're performing method development, trying to resolve compounds from each other. So if I just push this slide again, I'm hoping that works. You can see from the equation here that it makes sense to focus on selectivity because maximizing selectivity maximizes peak resolution. And we can see from this slide, I'm just going to see what 3rd and 4th are, that the listener suggested listed as part of the question. But this is a simplified slide. There is a great textbook out there, which is the Snyder, Kirkland, Dolan book, which I've cited at the bottom here. If you look at that textbook, if you get that, and you look at the page that I've quoted in the section from which this slide is derived, you'll see you can actually quantify the impact of these different parameters on selectivity. And you'll see that based around the information in those books, that these parameters are the most powerful parameters with respect to selectivity, which affects resolution and so on. And what we're trying to do is resolve compounds from each other. I hope that's answered your question. If it hasn't, please email me and maybe we can have more of a discussion on the phone or by email. That's no problem, but I'm hoping that's answered the question. Thank you.
Someone asks what I think is a related question on selectivity. How can someone tell if a peak in a chromatogram is actually coming from coelution of several peaks? That is, what would you suggest to do to test for this, providing the peaks look fairly symmetrical?
Well, if you are asked, so in the example I gave, the acetaminophen example, we were asked to develop this method, this related substances method, and all of the compounds were available to us. So we just needed to develop the chromatography. So of course, for us, we could run the compounds individually. So we knew where they eluted, and we needed to develop the method so that we could have full separation of all the compounds. That's the easy situation. Of course, the difficult situation is where you are given, which is a situation I'm very familiar with. I worked in the pharmaceutical industry for a long time. You have degraded samples, or you're given a sample that maybe there's one compound or two compounds that they know is in there, but there's a whole host of other stuff in there. In this example, selectivity is actually your friend, because you can use different column chemistries to try and literally, very crudely, count the number of peaks that you have in your samples under different conditions. So if you use the type of organic solvent, different column chemistries, the chemistries have to be different to each other, different mechanisms of interaction, and even different pH, so a low pH or mid pH or even a high pH, then you can start to build up a picture of the composition of that sample, even if it has many unknowns in it, because you can literally count the number of peaks. Now, the example I've put on the screen there is a simple LC-UV example. Of course, in real life, we use LC-UV-MS. So we can then try and understand molecular ions, some type of ion information, ionized information from the MS detector to help us track the peaks. So if you don't have MS, which many labs don't, and I didn't for many years, we use peak area to try and track our peaks across different chromatograms. But in an ideal world, you would use, and obviously UV absorption spectra if you have diode array detection, but ideally you use LC UV-MS, UV and MS in series. You build a picture around the UV data, the absorption spectrum, the peak area, and of course the MS data. That's always helpful, because then you can track your peaks across as they move around the chromatogram depending on the different conditions you're using.
Thank you. You mentioned using a 100 by 3 millimeter column for method development and stationary phase choice. After determining the correct chemistries from the development stage, do you change the column dimensions for the actual analysis?
So for us, it really depends on what we're doing. So good question, thank you. So our standard screen is the 100 by 3 mil 2 micron column. It's a good compromise of, because column length is directly proportional to the number of plates in terms of resolution. So 100 mil is a good choice for screening. The 3 mil ID means that we have a lower flow rate, which is always good for the environment. And the 2 micron particle size means that we get much better efficiency than 3 micron, but the back pressure isn't quite as bad as a 1.7. So that's why we use that format specifically. Whenever we then generate our initial screen, we will always try and develop the method on that platform. And then depending on what the person wants, sometimes people say to us, we'd like an HPLC method, we just translate that method up to HPLC conditions, 154.6, 3 micron, or sometimes we translate it back the other way and they want a UHPLC rapid analysis method, 50 by 2.1, 1.7 micron. Now I have a whole separate talk on method translations and how you can get a quantitative transfer of your chromatography irrespective of the column dimensions, if you use the right equations and you use the right tools. That's another separate talk. But yes, normally, to answer the question, we screen on this format, we develop on this format, but then depending on what the person had asked us for, we will either give them a method in HPLC or a method by UHPLC, or sometimes they don't care and they're happy with our screening format. So it depends.
Thank you for that answer. Someone asks, can these stationary phases be used for preparative separations?
Yes, they can. So these stationary phases have been designed to be fully scalable from 1.7 2 micron, 3 micron, 5 micron, and 10 micron, and we provide up to 30 millimeter ID. We also have some 50 millimeter ID stuff as well, columns for essentially semi-prep type activities. So everything from sub 2 micron for rapid analysis up to 10 micron with the same chemistry, the same silica platform as well. That's really important. Our silica platform is the same, right from the 1.7 right up to the 10 micron. This means you'll get the same chromatography, the same selectivity, the same chromatogram when you scale your methodology. So you don't need to do further tweaks as you change the particle size of your separation as you scale up.
Someone asks whether all 6 column chemistries are available for UPLC.
Yes, they are. So all 6 columns are available. Hopefully at some point, if you request the brochure, you'll see that all 6 column chemistries are available in 1.7 micron, 2 micron, 3, 5, and 10 micron. So it covers the whole range. And we make everything from 30 by 2.1 millimeter columns right up to 300 by 30 millimeter ID columns, 10 micron particle size. We make all of the columns ourselves. All of the material ourselves, so we can pretty much make any dimension that people generally want.
Referring back to an answer you provided before, someone asks if you use HPLC equipment with UV and MS as detectors, what would be your recommendation for the scouting gradient method to mimic the profiles presented today?
I would have to recalculate it. I mean, if you look at the equation that I provided, so if whoever's asked that question wants to download the slides, you can see that all of the conditions I provided are here. So if you're going to increase your column dimensions, say to 150 by 4.6, 3 micron column, for instance, that would change the VM term, which is on the screen at the moment. So then you just need to adjust solve the equation for the new values to give you the right gradient time and flow rates. It should be a simple calculation. If there's any problems, just send me an email and I can probably work it out for you and send it to you. Off the top of my head, I can't remember, because this is our standard platform is 100 by 3 millimeter 2 micron. But no problem, just contact me.
Somebody asks, do you have the outlined column chemistries in superficially porous particles configuration? So
we have a super C18 in the superficially porous particle, and we have a super phenyl hexyl, which is an aromatic phase in the superficially porous particle. Both of those column chemistries are also stable up to pH 11, from pH 2 to pH 11, but those are the only 2 chemistries that we do in solid core technology. So our approach for solid core technology has been to use a C18 base phase at low, mid, and high pH, and a alkyl aromatic phase, the phenyl hexyl, at low, mid, and high pH. So you're using pH as your selectivity tuner along with solvents and 2 column chemistries. So we don't have all of those chemistries on the solid core platform.
Someone else asks about the columns. What are the typical particle sizes of the 6 types of columns that you used for the scouting runs?
So the standard platform that we use is 2 micron. So this one that I showed here, you can see on the slide there, it says 6 times ACE column, 100 by 3 millimeter, 2 micron. That's our standard screening system that we use. We use that for all of our initial method development work, and then we make our decisions based on the data that we get from those first 6 screens.
Someone asks some questions about some of the examples you presented. How do you do peak tracking for the 10 compounds during screening runs?
So in this particular example, as I mentioned earlier, this was an example where we were asked to develop this related substances method, but we knew what all 10 compounds were. So this is, in many ways, as I've said a couple of times, this is an easier example because we had all of these species available to us individually. So therefore, we could run the individual components to make sure we identified the peaks properly. So that answers the question directly. For unknown samples, unknown compounds with LC-UV, it's a bit trickier if you don't have MS available, but you can still do it because I've done it for many years that way too. You use different column chemistries and you use peak area and try and map between the different chemistries, the different elution and retention times, and try and match the peak areas as best as you can when you have unknown compounds. But in an ideal world, especially for unknowns, you really do need ideally a single quad type instrument, an LCMS single quad instrument. Of course, anything more powerful than a single quad is great if you have that type of capability in your lab.
Okay. I think we'll just handle one last question. On the previous examples, how did you know the resolution was improved by alpha and not K?
Previous examples. I'm not sure which examples they're referring to.
Okay.
I mean, all I can say here is if I go back to this slide here, so you can see here that K, the green bar here, it increases rapidly up to a K of around up to nearly 10, and then it flattens out. So in terms of its impact on resolution, so K values can be meaningful and can be very useful when they are low in terms of their impact on resolution, but very quickly their impact on resolution is the law of diminishing returns. It very quickly plateaus, whereas you can see the red line for selectivity keeps rising with respect to its relationship to resolution. So chromatography theory very clearly tells us selectivity is more powerful with respect to resolution. But I'm not sure which example they're referring to answer it sort of explicitly, so I apologize for that.
Well, thank you, Alan, for answering those questions, and I want to thank the audience for submitting so many. We've had quite a bit of interest, but I'm afraid that's all the time we have. Thank you again for your fascinating presentation, and thank you, participants, for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you, On24, for technology and production services. And thank you, MacMod, for the sponsorship that made this interactive webcast possible. For CNN Webinars, I'm Ann Thayer. Have a good day.
Thank you.